If you replaced our sun with this star, its surface would swallow Mars, Jupiter, and reach past the orbit of Saturn. UY Scuti is 1,700 times wider than the sun, and your brain literally cannot picture how big that is. We're about to walk through the most extreme size comparison in the known universe, step by step, until the numbers stop being numbers and start becoming a feeling. From familiar planets to impossible giants, each jump will make the last one look trivial. By the end, you'll understand not just how large UY Scuti is, but why a star that enormous is already dying. Every scale needs a starting point, and ours is already enormous. The sun contains 99.86% of all mass in our solar system. Its diameter stretches 864,930 miles, so wide that you could line up 109 Earths across its face and still not reach the other side. Light itself needs 4.6 seconds to travel around its equator. Every second, the sun converts 4 million tons of matter into pure energy through nuclear fusion, producing 383 trillion watts of luminosity. It's a middle-aged G-type main sequence star, roughly 4.6 billion years old, sitting comfortably at the halfway point of its life. To us, the sun is everything. But in the catalog of stars, it's thoroughly, almost embarrassingly, average. Not all stars are born equal. A star's mass at birth determines everything: how hot it burns, how bright it shines, and how quickly it dies. Stars more than 8 times the sun's mass fuse hydrogen so ferociously that they exhaust their core fuel in just millions of years, not billions. When the hydrogen runs out, gravity crushes the core, temperatures spike, and helium fusion ignites. Then carbon, then neon, oxygen, silicon, each new fuel burning faster than the last. With every successive fusion stage, the star's outer envelope inflates, pushed outward by savage radiation pressure. The star becomes a supergiant, bloating to hundreds of times its original size. Its surface cools from blue-white to deep red as the photosphere stretches thin across an almost unimaginable volume. This is the pathway to becoming a red supergiant, and it's a one-way road with an explosive ending. In 1860, German astronomers at the Bonn Observatory catalogued an unremarkable variable star in the constellation Scutum, near the dense star clouds of the galactic center. It took over a century for anyone to realize what they'd found. UY Scuti sits roughly 5,600 light-years from Earth, deep in the disk of the Milky Way. Modern interferometric measurements reveal a radius approximately 1,700 times that of our Sun. That makes it one of the largest known stars ever measured. Its surface temperature hovers around just 3,365 Kelvin, cool enough to glow a deep, smoldering red. Yet because of its staggering size, UY Scuti radiates approximately 340,000 times the sun's luminosity. It is a pulsating red supergiant, rhythmically swelling and contracting, shedding mass into space with every breath. Let's build this visually. Earth is a marble. Beside it, the sun is a 6-foot beach ball. Now replace the sun with UY Scuti, and its surface extends past Jupiter's orbit, a sphere nearly 11 astronomical units across. A commercial jet flying at 560 miles per hour along UY Scuti's equator would need over 2,700 years to complete a single lap. Light, which circles the sun in 4.6 seconds, would need over 2 hours and 10 minutes to circle UY Scuti. You could fit nearly 5 billion suns inside its volume. Think about that. 5 billion copies of the star that dominates our entire solar system, packed into one object. If UY Scuti were hollow, you could pour in all 8 planets, every moon, the asteroid belt, and the Kuiper belt, and they would rattle around inside like dust in a cathedral. Here's what makes UY Scuti truly strange. Despite being 1,700 times wider than the Sun, its mass is only about 30 times greater. That means its average density is absurdly low, roughly 1.3 times 10 to the negative 6 grams per cubic centimeter. For context, that's over 1,000,000 times less dense than Earth's atmosphere at sea level. The outer layers of UY Scuti are closer to a laboratory vacuum than anything we'd call solid or gaseous. You could theoretically fly a spacecraft through its outer envelope and barely notice the matter around you. This extreme low density is precisely why UY Scuti is unstable. Its gravity can barely hold on to its own atmosphere. It's losing mass at a ferocious rate, roughly 60 times 10 to the negative 6th solar masses per year, bleeding itself into a vast surrounding nebula of ejected gas and dust. UY Scuti isn't without competition. Stephenson 2-18, a red supergiant in the Stephenson 2 cluster near Scutum, may be even larger, with some estimates placing its radius at over 2,150 solar radii. WOH G64 in the Large Magellanic Cloud spans roughly 1,540 solar radii. And then there's Betelgeuse, the famous shoulder of Orion, at around 764 solar radii. Massive and dramatic, but less than half the size of UY Scuti. The challenge with all these measurements is that supergiant stars don't have crisp surfaces. Their photospheres are diffuse, pulsating, and shrouded in dust. Measured radii can shift depending on wavelength and observation epoch. What's clear is that we're approaching a physical upper limit, a maximum size that stellar physics will allow before a star simply tears itself apart. UY Scuti will not last. Red supergiants occupy the final chapter of a massive star's life, a chapter measured in hundreds of thousands of years at most. Deep inside, the core is almost certainly fusing heavy elements, racing through a sequence that ends at iron. And iron is the wall. Fusing iron consumes energy instead of releasing it. So once an iron core forms, it grows until it hits the Chandrasekhar limit of roughly 1.4 solar masses and collapses in milliseconds. The result is a core collapse supernova, an explosion bright enough to outshine an entire galaxy. Everything UY Scuti has shed into space will be blasted outward, seeded with elements forged across the star's entire life. The carbon in your bones, the oxygen you're breathing right now, came from a star that once faced this exact fate.